Hello, I'm Anulewicz, and this is my lab report for A2610 digital sampling. So first we have our data from prior to week 2, which is waveform identification. For this you can see how for sample 1 was single sign, sample 2 was single sign, sample 3 was a triangle sine wave, sample 4 was a square sine wave, sample 5 was sine, sample 6 was a ramp, sample 7 and 8 were both single sign with white noise, sample 9 was a sum of 3 signs, sample 10 was a product of 2 signs, sample 11 was sine of signs. And you can see the peak period frequencies and power levels at peak period frequency for each of these in the table listed. But note for samples 4, 6, and 9 that there were additional ones as well, with sample 4 having peak period frequencies at 1,000, 3,000, 5,000, 7,000, 9,000 hertz. Sample 6 having peak frequencies at 1,000, 2,000, 3,000, 4,000, 5,000 hertz. Sample 9 having peak frequencies at 100, 1,000, and 10,100 hertz. And the corresponding peak power levels are listed next to those, which you can pause and read. Next, we have our supplemental questions. First was for the product of signs is frequency waveform based on the period of the time as any frequency of the power spectrum, and not exactly, but 2 of our frequencies summed up to the peak of 1100, which reoccurs in the power spectrum graph. So I would say that it did show up for that matter. For triangle waves, the period of the waves seem to be exactly inversely related to the frequency, which makes sense as period should be 1 over frequency. And the triangle waves appear to have more power at higher frequencies, which goes against what I predicted, as square waves should have more power at higher frequencies due to it taking more power for them to maintain that long flat square shape at the top of their height, because they're just holding it steady. It takes more power to do that, just to go up and then drop right back down. When volume is set to max, the square waves look very heavily square, and as volume is lower, it's observed that the amplitude decreases while period and frequency remain exactly the same. We determined that track 2 was our 1 kHz sine wave, and the major takeaway was that record length is exactly double the number of discrete points present. So for a record length of 14, you have 7 discrete points. For 8, you have 4. 6, you have 3. 4, you have 2, and so on. When you go higher or lower, you'll notice the trend carries true. Now we have our observations for track 9, which is our sum of 3 signs, and a record length of 500 at various sampling rates. And the main thing to note here is how at frequency 3, once you hit 20,000, sampling rate of 20,000, your frequency does not go above 10,000 hertz. Next, we notice that track 7 and 8 are sine waves with white noise, with track 7 having a signal to noise ratio of 5 and track 8 having a signal to noise ratio of almost exactly double that at 9.7. It should theoretically be 10, but it's not, because likely due to errors reading the graphs to get our numbers for our ratio calculation. Finally, we scored the implementation of a low-pass filter for the sum of 3 signs in track 9, and we noticed that cutoff frequency required was 4,239.44 hertz, which is determined because it was where a single sign would appear for the Chan zero filter curve in the E versus time graph, and where the filter frequency at 10,000 hertz became a flat line. Now we have my experiment. So my motivation for this is my mom was from New Orleans, and growing up, jazz was a huge part of my household, with myself loving the horns and brass instruments the best. So this motivated me for the experiment, as I wanted to see how the waveforms and frequencies produced by different brass jazz instruments playing the same notes would appear, and if the differences were a reason why they sounded so good together. So my goal here was to determine differences in frequencies and peak power for different brass instruments playing the same notes, as for the trumpet, trombone, and saxophone, which are the 3 key brass instruments in a jazz band. And to perform this experiment, I used an online electronic trumpet, trombone, and saxophone respectively, and played each note through a 3.5mm audio jack so the DAQ could pick it up. My procedure was I set up this by connecting a 3.5mm audio jack to my laptop and tested to make sure I was working with simple DAQ software. My sampling settings are seen below. For my procedure, I took each digital instrument, played the note required for 5 to 10 seconds to ensure it was fully picked up by the software, and used the hold feature to capture a still image of the waveform graph in order to do analysis. I repeated this procedure for each instrument for each of the 7 notes. With this, I was able to use the fundamental frequency for each note to determine how harmonics and overtones impact the waveform of each instrument when playing the same note. Now we have my data and waveforms. Feel free to pause on these to get a better view of it. The trombone will always be the top left, trumpet is always top right, and saxophone is the middle. And this is for C4. For D4, for E4, for F4, for G4, for A4, for B4. And now we'll go into analysis for this. So note how for each graph, the waveforms have the exact same general form, shape, and frequency due to the fundamental frequency, but they look different due to their harmonics and overtones. So this means that the waveforms are similar shapes with peaks and frequencies and valleys in the same order and magnitude, but differentiated by what is overlaid. So for example, I'm going to show this graph right here. You can see how the black is the fundamental frequency, but as you add in all the harmonics which occur in each instrument, and they're different for each one, you get a different resulting graph, which is what leads to these odd troughs and values we see while maintaining the exact same frequency. And note, and our fundamental frequencies are calculated below. It is the exact same for each instrument for their corresponding notes. And you can see how, for the most part, our experiment was slightly above, with one case being a little bit below, which is due to the graphs not having perfectly accurate crosshatches for me to read and make calculations based off of. But you can see how the experiment is very close to the expected, showcasing the accuracy of the DAQ software and my data. So some complications and errors that I discovered here. One possible error could be using virtual versions of the instruments instead of the real thing, as digital feedback and analyzing a recording of the real thing may have slightly impacted the frequencies observed, which explains a slight difference between expected and experimental. And I experienced slight issues occasionally with the feedback when testing the audio jack initially, but I found a solution by using the USB-C to 3.5mm converter. But even with this, some lingering feedback may have possibly remained, which could have explained some of these slight discrepancies or impacted my data. Finally, here's my conclusion. So as proven before, while each instrument shares the exact same fundamental frequency, they have different harmonics that result in different waveforms. So the trumpet is characterized by sharper, more jagged waveform with rapid changes, which is because of how a trumpet produces stronger and higher harmonics, which creates more rapid and aggressive changes. On the other end of the spectrum, you have the trombone, which is the smoothest waveforms of the three with a more rolling pattern and slower oscillations in comparison. This is because how a trombone has fewer and lower and less pronounced harmonics, which result in a smoother waveform. Finally, in the middle is the saxophone, which has very complex waveform, while it's just more rolling than the trumpet, but less sporadic. And this is because of how the saxophone is able to produce a mixture of high and low waveforms, which create a very complex, but less sharp and slightly less aggressive waveform. And this is the reason why, to conclude for why these instruments work so well together, is because of how they have the exact same frequency. The notes don't sound out of sync or unharmonious, but by having different harmonics and different lower and higher notes, it creates an almost ensemble of the exact same frequency, but in different levels, making a nice classical jazz sound we know and love. And here are my sources for this. Thank you so much for my lab. I hope you enjoyed.